Oh, thanks, host. Yeah, welcome everyone for to the third lecture. Today we'll talk about coupling multiple probes to the field and try to implement quantum information protocols. So basically, it's what I said is that we now rely on two or more detectors in order to transmit information from one place or from one local region to another local region. So rely on two or more detectors. So we will consider these two detectors or more, but basically the picture that you should have in mind is that if before we consider some situation where one detector would couple to a local region around a trajectory, now we want to basically see what happens when after that, a second detector couples along another trajectory in another region. And if we want to transmit information in the standard sense of the word, then we want the other the receiver basically, or the the other system. In this case, let's use A and B. So system B or Bob, if you will, to couple after or just couple in a region that overlaps the causal future of the interaction region of Alice. Okay, so Alice would have her own coupling region here, a lambda A of x, which is the spacetimes mirroring function. Bob would have his here. Each one of them is coupling a detector to these different regions, and we want to see how much information or how can Alice transfer information to Bob. Okay, that's our main idea. So basically, each one of these detectors will have their own Hamiltonian. We're going to restrict ourselves still to qubit detectors. We're going to talk a little bit about how to generalize this in the last lecture, but we're not going to go into details because this is a good enough toy model so that most of the features of the theory will be available here or will be present already in this case. So basically, we're assuming here that both Alice and Bob, each one of them, they have their own notions of proper times. They have their own free Hamiltonians. Each one of their free Hamiltonians, that they generate time evolution with respect to their own proper times, right? So these are the free Hamiltonians for each one of them. Free Hamiltonians. And they generate time evolution with respect to the respective proper times. So this is important because each one of the qubits basically will be defined according to one trajectory. Each one of these three Hamiltonians are the proper Hamiltonian that, as we discussed last time, would be seen by an observer that is co-moving with these trajectories. Okay, and these proper times, the tau A and tau B, I'll still assume that they are the Fermi normal coordinates. So Fermi normal times associated to each trajectory. Again, more details about this will come soon, but what matters is there's an extension of the proper time of each one of them to a time coordinate that is locally defined around the trajectory. Cool. And same as before, the interaction of each one of them, so the interactions will be prescribed by this interaction Hamiltonian density. So the interactions, say with the field, with the quantum field phi of x, these interactions, they are prescribed by an interaction Hamiltonian density, which basically combines the interaction Hamiltonian density of each one of them. So the idea is that the total interaction Hamiltonian density in this case is simply going to be the sum of the interaction Hamiltonian that Alice had with the field with the interaction Hamiltonian that Bob has with the field. So this is literally two of the same model that we had of the models that we, two of the model that we saw before. Each one of them coupled to the same quantum field, but in different spacetime regions associated to different trajectories and things like this. And in this qubit case, you can, like, each one of these are e to the I omega a tau a, and you're going to have the sigma plus a, and the same thing here, but with the conjugates. Of course, the same thing for Bob. So this will be also pretty much the same thing, but with a exchanged by B. Okay. So we have our full Hilbert space here is the Hilbert space of two qubits, right? So the Hilbert space is basically a Alice's Hilbert space, Bob's Hilbert space. And if you pick a specific representation for the field, like a Fock space here for the field, like a Fock space, of course, you don't have to pick the representation for the field because we're always tracing over it in the end anyways. But if you want to, like, just keep in mind where these things are defined and everything, basically there's always a tensor product here, right? This first term here, there's a tensor product with B, and there's the identity acting in the Hilbert space of B here. In the second term, there's the identity acting in the Hilbert space of A. So this is a C2 times C2 system. And then in the end, we have the quantum field, right? That's basically what our Hilbert space is. And same as before, what we want to do is to start with initial states, and we want to find out what are the final states in this case. And this will allow us to say what is possible for Alice to transmit to Bob, or for the final state of Bob to be, basically. Okay. So same as before, we will consider that everyone starts uncorrelated. So start that the initial state of the whole interaction is rho A0, rho B0, and rho omega, which the same as before. This is a quasi-free state, which is the zero mean Gaussian state. Now what we need to do is to compute the time evolution operator, and we'll see that it's considerably harder to perform the calculations in this case. But and I'll skip a little bit the calculations. I'm not going to do all of that in all generality. But at the same time, now we get some much more interesting phenomena, right? So the time order exponential is so the unitary time evolution operator is also the time order exponential of this Hamiltonian. Now, well, what is the time parameter that you pick to time order this? I'm going to say that this matters very little, but it matters. But we're not going to talk about this for now. We're just going to pick any time parameter, and we're going to pretend that it's correct, and then we're going to discuss more about the issues with this again the last lecture. But for now, let's just implement the things and compute what we need to compute. So this final state of the detector, as we had before, it's just going to be the trace over the field of this UY rho 0 UY dagger. And we're going to use the Dyson expansion first for computing this. So this is going to be a UY1, UY2, which is given by the integrals of the Hamiltonian density, and then the time order integral of the Hamiltonian density and everything. Nice. So it's kind of annoying to compute this because we're going to get many terms. I'm not going to write down all the terms here. We're going to write one just to convince you how annoying this would be if we wanted to do exactly the same thing that we did last time. So say that we wanted to compute the term, which is the first order term with the rho 0, and then the first order term dagger, okay? Which is one of the terms that was important yesterday and would also be important in this case. So this would be lambda squared. Then we would have the integral dv prime, basically because you're hitting the rho zero from both sides with the interaction Hamiltonian density. And what you would get would be the lambda a of x, mu a of tau a, plus lambda b of x, mu b of tau b. And you would multiply this by rho zero d. Sorry, yeah, by the full rho zero actually. But I'll leave because we're already tracing over the field, I'll skip this part. But so basically what we would get here, already skipping a couple steps, would be something like this: mu a of tau a prime plus lambda b of x mu prime mu b of tau b prime. And then there would be the state of the field contracted, basically the trace over the field of the two quantum fields that would show up in each case, which would give you phi of x prime, phi of x, because you'll have to, well, basically, let me write this in a way that's probably more clear than this, which is just to say that the trace over the field is only going to affect the trace over phi. It's going to affect the part which is phi of x, the rho of the field, phi of x prime. And here this rho zero d, what I mean here is rho zero a times rho zero b. Okay. So this is one of the terms that we would have to compute. If we were to do the same thing that we did last time, the basic, which basically was to say this is e to the I omega a tau a sigma a plus Hermitian conjugate, and then we would have to expand all of these, expand all of these, expand all of these, expand all of these. There's 4 terms on each side. They're gonna hit the row from different sides. You're gonna get 16 terms. Each one of these terms multiplied by this term here is simply the Weidmann function, right? This is the Weidmann function of x prime x, because you need to have the row, you have to change the order in the trace. But you would get 16 terms. So again, annoying calculation to be done, right? But we can just rewrite this term in a way which is a little bit more, it's a little bit more convenient, let's put it this way, which is basically to say that this term is the integral of lambda squared dv prime. Now we're going to rewrite this as a sum over I, where I can be A or B. I'm actually going to use capital I because we're using capital A, capital B. And S, call it S1, which can be plus or minus 1. And what I'm going to write here is lambda I of x e to the S1 omega I t sigma S1. And this term here, now, this is not a t, this should be a tau I, but this term here is going to give us exactly what we would get from so if I equals A, the plus or minus will give us both terms that we get expanding the mu. And if I is B, then we also get the two things. We're just using a convention such that this sigma I is plus or minus 1 is just plus or minus. But to be honest, nothing prevents us to just coming here and erasing this 1. The sum is over S equals plus or minus, and this works with everything because the S just gives the sign. But now if we write it like this, then we have this times our rho zero d, and then we're going to have exactly the same term here, the same sum, because this is exactly the same Hamiltonian. So this will be a sum over J equals AB. The S2 equals plus or minus lambda J of x e to the S2 omega J tau J sigma J S2. And all of this would be, of course, times the Weidmann function at x prime x. So in the end, if you bring all of these sums together, what you'll find will be the sum over I and J equals A and B. The sum over S1 and S2 equals plus or minus. The rho will now completely factor with the sigmas. And the integrals will basically be the integrals of the the Whiteman with the lambdas, right? So this would be sigma I S1 rho 0D, sigma J S2, and everything else, which is space-time dependent, is now going to show up integrated with the Whiteman function. Just move this a little bit down. And everything else will show integrated with the Whiteman function here. And this will be lambda I of, I'm going to actually bring the dex primed version here before, because dex prime is the first argument of the Whiteman. So this is lambda j of x prime. These should be primed. Apologies for this, right? They were primed up there. So e to the s2 omega j tau j prime. Then we're going to have the lambda I of x e to the s1 omega I tau I w of x prime x. Sure, it's a big expression, but in the end, all of this is just the Whiteman as a bidistribution evaluated at lambda j s2 lambda I s1, right? So we're here, I'm defining lambda I s of x. It's basically the lambda plus or minus that we had from yesterday, right? So this is lambda I of x, and then you get the e to the I s. Oh yeah, I forgot some i's everywhere, right? There's an I in each one of these phases. So e to the I s omega I tau I. So this is the plus or minus, lambda plus or minus. So in the end, this term would contribute with yes, a bunch of terms which are being summed together, but you can just cast them all as a sum of terms which are, again, this Whiteman function, this Whiteman by distribution applied to the space-time regions. So W lambda J S2 lambda I S1, and then here you're gonna get the sigma matrices hitting on the initial state of the detector. In the opposite order is the Whiteman function. And I'm not gonna bore you and do the calculations for the other term that we need to compute, which is the trace of phi of ui2 rho 0, which is another term that we have to compute. I'm just going to tell you that that if you were to compute this, you know what? Let's just look at the first expression, and hopefully I can convince you of what the final result is. So here we're going to have a time ordering parameter. I'm calling it t. You can call it something else if you want. But it really went to the side here. Sorry about that. Right. So this time ordering parameter t, which can be whatever you want. Then you're going to have the product of two interaction Hamiltonians. This is lambda a of x mu a of tau a plus lambda b of x mu b of tau b. And now you multiply this by the interaction Hamiltonian before, multiplying by the density operator of the qubits. This is basically the only difference. Plus lambda b x prime mu b tau b prime rho 0d. And then there's the whole part that depends on the quantum field, which in this case is going to be a trace over phi, and you're going to have the field coming from the hi, the field coming from the hi prime, and the rho of the field. And this is already the Whiteman function, right? This is already the w of x prime. So basically, what's going to change here is we're going to use the same strategy. We're just going to write these as sums of the plus or minus and the I equals AB, IJ. Well, now we have this heaviside theta. And the order of the arguments that will show up in the y-point will be different, and the sigmas will be multiplying from the left always. So basically, if you do this calculation, what you will find will be minus lambda squared, the sum S1, S2 equals plus or minus, ij equals AB. And now we don't have to flip the arguments of the Whiteman. Notice that here it's wxx prime. We had w of x prime x before. So here, what we're going to find, let me just put this a little bit more down. What we're going to find here is wt, because we have the heavy side with the Whiteman, evaluated at lambda I S1, lambda J S2, and these will come with the order of the sigma matrices that hit the row in this case. So I S1, sigma J S2, row 0 D. And of course, if you wanted to compute the last one, the last term is just going to be the conjugate of this one anyways. So just going to explicitly say that this is the same as the trace over phi of uy2, row 0. Nice. So now basically we have the final result, which is just adding together this sum here with this sum here with the other sum, right? So I'm just gonna write it down, what the sum is. And then we're going to see one explicit example where which I guess it's kind of natural to try to see what happens in that case. So the final state of the detector will then be given by whatever the initial state was, because this is perturbation theory, plus lambda squared. And then in every single one of these three terms, we're going to have the sum over S1 and S2 equals plus or minus, the I and J equals AB. And here we're going to have the first term that we had was a WS1 lambda. I'm changing the I and J and the S1 S2 in this case just to, well, you could keep it there, it doesn't really matter. But in my mind, it looks a little bit nicer if we do it like this instead of the order that we used before. See, because before we used the S1, S2, and well, whatever. Minus Wt of the lambda I S1, lambda J S2. And here we're going to have the lambda I S1, lambda sigma I S1, sigma J S2 hitting the row 0D. And then we're going to have the last term, which is going to be a Wt of the, yeah, I'm not going to flip anything here. I'm just going to write this as being the conjugate, and I'll flip the other one and conjugate everyone. So, okay, so this will be the star. And the other one here, we're going to get row 0D and a sigma. So notice that the star hits everyone here. Now here, we have to flip the order and to conjugate them, right? So the sigma J that was here is going to come here. The sigma I is going to come here. The dagger of the S2 will change the S2 to a minus S2. Not that it really matters too much, but we're going to get this in the end. And this will be the final expression that we have. So this is basically the quantum channel that maps the initial state of the detector rho 0D to this final state to leading order in lambda. Okay. Okay, nice. We spent a while doing calculations. We spent what, like 20 something minutes doing these calculations. Now, what can we actually extract from them, right? I think that's the key question. So if we, I think that a pretty natural example to consider. So going back to the picture that we had up there, okay. So now, what if Alice starts with her qubit in the excited state? She interacts with the field. Maybe she dumps this excitation into the field. This excitation would propagate and then reach B, and then Bob could be in the ground state, say. And then it's possible that Bob would become excited because Alice dumped this qubit into the field. Okay, so let's explore the situation. Let's see what happens. Okay, so this would basically correspond to the idea of getting rho sorry, A0 being in the excited state. So we want Alice to be excited and to try to dump her excitation into the field. So EA EA and Bob. Uh, let's see what would happen if Bob started in the ground state, so that he could perhaps get excited by whatever Alice deposited into the field. Right. So now we would have to basically see which terms in the above sums are non-zero, right? And then we would have to write down everything and yeah, and yeah. I in the notes that I'll post later tonight or maybe tomorrow morning, probably later tonight. You can really see which terms would be non-zero, whatever. I'm just gonna write the final result for this. If you really compute this, basically using the fact that the sigma plus I is equal to zero, right? And all of the conjugate versions of this, whatever. But if you use this, then you can get rid of many terms. Um, only 12 terms matter. It's 4 terms in each one of these. But you don't really have to compute these ones because these are all the Hermitian conjugates of the previous one. So you don't really have to compute these last ones. In any case, what you're gonna get in the end, if you compute all of these things, is so your rho D will be the rho zero. This rho zero will be, of course, the product of the sigma A plus, sigma A minus, sigma B minus, sigma B plus the correction, which is second order. And this correction is going to have a couple of terms. Some of them combine, some of them cancel, but in the end, the terms that will survive will be these. And here I'm going to use the shorthand notation WA. Well, I'm going to define it soon, but this basically W evaluated lambda A plus, lambda A minus, right? It should be kind of intuitive, but I'll definitely write that down later. So sigma plus sigma A minus, and once things started lagging, I just restarted the stream and everything. I restarted the screen share and everything went back to normal. So hopefully that's gonna work. Yes, perfect. Okay, cool. So sigma B plus, sigma B minus. Here we're gonna get a W B B minus plus. So these are these are two of the diagonal terms. There's still one more diagonal term to go, but these terms I would just like to comment that this is the W lambda B minus lambda B plus. And we saw this term yesterday, right? This is the vacuum excitation probability. This is the vacuum excitation probability of B. So of someone, of a detector that has energy gap omega B that interacts in the region lambda B. And this other one here, you say that the plus and minus are flipped. This is basically the D, sorry, this is the yeah, this is the de-excitation probability because now you flip the sign of the omega, which, as we discussed briefly yesterday, if you flip the sign of the omega, it's as if the ground state was the excited state and the excited state was the ground state. So this is the de-excitation probability for Alice, basically. This is the excitation, this is the de-excitation. The other diagonal term that we get, the other diagonal term that we get is basically the one that has to be because the density operators always will have trace 1. And if you complete the trace of this right now, the initial state for the detector has trace 1. Then I have a lambda squared, these two terms. So now I'm going to subtract these two terms. So notice that this is just the initial state for the detectors, right? This is just the initial state of the detectors, and the terms that you get here are WA plus minus plus WB minus plus, which is exactly what you need to in order to cancel the trace so that the trace of this is still 1 which is the trace of row 0. So whatever you add using the Dyson series will always be traceless, okay? To all orders in perturbation theory. Nice. Then we have some other terms. We have some correlation terms, which are a little bit more interesting. But we're going to see very soon that they're not as interesting as one would like to have. Because basically, so far, what we have is Alice is getting excited, Bob is getting excited, but there's no connection between the two. There's just no correlation between the two. There's no information being exchanged between the two, right? And then we're going to get two terms, which are the Feynman propagator terms. So minus G, sorry, let me write it in the same order that I had it before, which is having the sigma A minus sigma B plus G. G stands for the Feynman propagator. Again, I'll define these things very soon. And minus again. Minus sigma A plus sigma B minus G A B minus plus conjugate. And of course, we get the other terms, which are for the lambda to the 4th, assuming was a free state. Cool. So how do we put this into a density operator? Maybe that's more intuitive. And after doing this, let me just write down the density operator. So the density operator will be lambda squared WA plus minus, which is the excitation probability. We're going to have a 0, a 0, a 0. Then we're going to have here G A B minus plus, because this is the term that is associated with so the easy way of seeing this is like sigma A minus is always going to be talking about the bottom part here for A, and sigma B plus is always talking about the upper part of the submatrix. Okay, so this is how you compute this. So sigma A plus, sigma A minus, sorry, this term, sigma A minus sigma A plus is the projector in the ground state, which is up here, and then here's the projector in the excited state for Bob, which no, I think that this is in the wrong spot. So this up here is a projector in the ground state. This up here is a projector in the excited state, which is in the bottom. So basically, yeah, this should be here. WA plus minus. Nice. This one here is talking about this part here of the matrix, and the sigma A, and sigma B plus is talking about the upper part up here. And basically using this logic, you can put all of the terms. This term here is the initial state, which is Bob is in the ground and Alice is in the excited. So Alice in the excited, we're talking about the bottom half. Bob's in the ground, we're talking about the upper half. So 1 minus WA plus minus WB minus plus. The 1 comes from the rho 0D, which is the initial state. The minus, these two come from here. Then we have the WB minus plus, which is the other term that makes the trace be 0. And of course, you can confirm that this is Alice being in the bottom, and then Bob also being in the bottom. So bottom. Let's just compute the other terms here, and then the rest of the terms will be the conjugate of the other ones, basically, right? So this this WBA minus, it's here. I'm forgetting to put the lambda squared. Sorry about that. But this WBA minus is going to be here, which is Alice in the bottom here and Bob in the bottom here. So WBA minus minus. And here we just have the conjugate of these two terms, and the other terms are all 0. Right? So this would be the density matrix for this. So the density matrix, of course, in the basis, ground Alice, ground Bob, ground Alice, excited Bob, excited Alice, ground Bob, and in excited Alice, excited Bob. So this is the basis. And okay, the last thing is that Wij plus minus, well, let's say S here. S1, S2 is just being used to denote W of lambda I S1, lambda J S2, and the the G is the Feynman propagator. So if you use the properties of the WT, the W minus T, and the conjugates, you're going to be able to factor all of these into Feynman propagators, and you're going to get something like this. All right, nice. Now, this is the calculation for this particular case. So let's go back to the question, which is, what can we actually measure with this? What or what can Bob learn from Alice? Would it be possible for Bob to actually absorb some energy that Alice deposited into the field? That is the question, right? So if we want to find out what's the sorry, this WA. Now I'm a little confused, but I think it was right before. It was right before, right? Because then, yeah, both Alice and Bob are in the, yeah, never mind. This was right before, which is the projector in the, yeah, sorry about that. That's projector in the ground state for both of them. This is where this one should be. WA plus minus. There you go. Because now if we want to find out what is the final state of Bob, it's enough to partial trace this matrix over the big matrix. So remember that this is this block form because this is the tensor product of two C2 by tensor C2 matrices. So if we want to see what is the final state of Bob, so what is the final state of Bob, then because Bob is associated with the inner structure of the matrix, basically what we have to do is to take the trace of the blocks, which is to add this matrix with this matrix. Okay, this is the trick that gives us the final state of Bob. So what do we get if we do this? Well, rho B is just going to be the sum of the matrix above, which is the lambda squared WA plus A minus 0, 0, 0, plus 1 minus lambda squared WA plus minus lambda squared WB B minus plus. Go to lambda squared WB B minus plus. And if we compute this, what we find in the end is that Bob that started in the ground state, his final state is now given by this. Now, if you have computed, sorry about the erasings here. Fix this. There you go. Now, if you remember yesterday, when we considered also if you remember this, the excitation probability. So in the end here, okay, we compute this excitation probability, right? We compute the final state of Bob. What we find is a state which is exactly what we found yesterday when a particle detector is interacting with any operator of the field. So Bob cannot see Alice, right? This is what this means. Nothing here depends on Alice. Absolutely nothing here depends on Alice. So if nothing depends on Alice, this means that it's impossible for Bob to get excited to leading order. Okay, so this means that if you just use the setup that we considered before of like the two folks and Alice interacting here, Bob interacting, well, anywhere to be honest, in any interaction region, we just concluded that to leading order, it's not possible for Alice to even affect Bob if Alice starts in the excited state and Bob starts in the ground state. Now, this is kind of weird that this happens, maybe you think, but there's a clear explanation for this, okay? So what happens here is, so this is independence of Alice's. And the reason for this is that A's effect on the state of the field will change the field state so that the Whiteman function is going to change to a Whiteman function plus a lambda squared terms and a change that depends on Alice. Okay. Now, Bob only sees like W of lambda B minus lambda B plus. Whatever state of the field, whatever state the field is at when Bob interacts with it, Bob will only see this term, which is the excitation probability. That's a calculation that we did before. So basically, and the worst thing is this comes with a lambda squared. So now, after the fact, after Alice affects the, so after A's interaction, Bob sees lambda squared W of lambda B minus lambda B plus an effect which is a fourth order in the coupling constant. Because the change here, W plus lambda squared, whatever Alice does, we'll just add that lambda squared to this W that is already multiplied by lambda squared. So in the end, Bob will be unable to see any change in the field. Now, okay, is this general though? What is actually causing this? What is the reason for this? Okay, the reason for this is that both Alice and Bob are starting in states such that the expected value of the interaction Hamiltonian in A is 0, and the expected value of the Hamiltonian density in B is 0. What I mean here is, you remember that the mu A is basically it's the sigma x, right? Sigma xa. And if you start in the ground state or in the excited state of a Hamiltonian, which is in the sigma z direction, then now the expected value of this mu A is going to be 0 there. So by picking Alice and Bob to both start in the excited and ground state, this means that the actual interaction starts at its smallest possible value. That's why we need to go one extra order in perturbation theory in order for Bob to see an effect in Alice. Because first the field has to affect Alice's state a little bit toward her lambda, then Alice's state change toward the lambda. Now we'll make this expected value be non-zero, but this expected value will be of order lambda squared in the end. Okay, the effect that it has. Or yeah, when you do the product of the Hamiltonian with itself in the time evolution operator, you get something which is of order lambda squared. So basically, if you start with Alice and Bob in the ground or excited states, perturbation theory will tell you that that what you'll get in the end is that Bob doesn't see Alice to leading order. Okay, to higher order, of course, yes, but then to higher order, then the calculations really become very annoying to higher order. So how do we handle this? Well, of course, we can consider general initial states, right? So that's what was done in 2014, and I'll just give a summary of the results. So in general, if the initial states, if the initial states for Alice and Bob are psi A for Alice, which is a general pure one qubit state, which has coefficient alpha in the excited and beta in the ground. And basically the same thing for B. Psi B is also an alpha B, excited B, plus beta B. Oh, this was beta B ground B. Now, it can be shown that, so you can compute this, but people have computed it before, and it's pretty annoying to go back there with general states, whatever. It can be shown that if you go to the archive 1405.3988, the state probability okay, which is the block of the order. This PB, let me write the B more properly. So the PB is given by alpha B squared, which used to be the coefficient, the excitation probability anyways, like that excitation coefficient anyway. So this is the order 0 term, plus an RB, which is a term that only depends on B, and an SAB, where, oh, okay, where the SAB is given by, oh, sorry, we'll just restart the screen share again because it's, yeah. So where the SAB is given by 4 lambda squared, the integral dv prime, of course, like plus order lambda to the 4. Then here you're going to get lambda a of x, lambda b of x prime. Now there's a term which combines the alpha and beta coefficients for Alice, e to the I omega a tau a. This will be multiplying a term which is the real part of now something which mixes the alpha b and beta b, and then e to the I omega b tau b prime. And now the big thing here is that you get the field commutator here, which is the I times the E, which is the retarded minus advanced propagator, right? This is the field commutator. So this is the 2 phi of x, phi of x prime. And there we go. All right, now the RB term, I mean, it's not really important because it's also independent of Alice, but it's basically the coefficient associated with the ground state of B times the excitation probability and the coefficient associated with the excited state with the de-excitation probability, where basically the PB of omega is the integral dv prime of lambda b of x, lambda b of x prime, and we have the e to the I omega b. Sorry, not necessarily omega b, just the omega, which is what's going to give us the excitation or the de-excitation probability. Wow. Which is what's going to give us the excitation or the de-excitation probability. So this is e to the I omega tau b minus tau b prime with a minus sign, and of course the Whiteman function. So this is why we get the excitation probability associated with the coefficient beta b squared, which is where the coefficient associated with the ground state. So probability of being the ground times probability of getting excited plus probability of being the excited state times the excitation probability, which is the minus omega thing. And of course, there's this SAB term, which is the term that depends on Alice. Notice here that if alpha b or beta, sorry, if alpha a or beta b, sorry, if alpha a equals 0, or if beta a equals 0, which is the case in which Alice starts in the ground or excited state, the same thing is true actually if alpha b equals 0 or beta b equals 0, then SAB is 0, which means that then again, B can see to second order the influence that Alice has in the state. Okay. So basically, you need both of them to have some component parallel to the interaction, basically, so that with the field, so that they will be able to signal to each other. Okay, so this means so A can indeed affect the excitation probability. Basically, A can affect B, provided that they start in states such that the expected value of the interaction Hamiltonian is not 0. Okay? Cool. So, important. This only happens if they are causally connected. In here, there is the explicit assumption that so here there is the explicit assumption that the interaction of A happens before the interaction of B. So basically, interaction of A happens before the interaction of B in these calculations. What I mean here is basically that the formal statement is that the interaction of B does not overlap the causal past of A, but if you have a time, a coordinate time in Minkowski spacetime or something like this, then you'd be able to phrase it to weaken this condition and to phrase it differently. But the idea here is remember that this E is the GR minus GA, right? So it's the retarded minus advanced propagator, which means that if here is X prime, these are the regions where E of X prime can be non-zero, okay? So here you're basically if the interaction of A happens before the interaction of B, you need them to have an overlap Like you need them to be causally connected, otherwise this term here is going to be zero. If they're space-like separated, then definitely this SAB term is going to be zero, uh, uh, and A is not going to affect B at all. Okay. So basically it's you need them to be causally connected so that A can affect B, or can so that B can realize that um the interaction with the interaction that A had happened. Okay. Cool. So with this, this allows Alice to send classical information. So this allows Alice to send classical information to Bob. Basically, the idea is that you can send information by either coupling or not. So by either coupling to the field or not. And now if she decides to couple, then Bob's excitation probability is going to change. And if she decides to not couple, then Bob's excitation probability will remain the same. Okay. So if Alice decides to do this using perturbation theory, then she will affect the very small the excitation probabilities of Bob very, very little. Okay. So basically, this is a very noisy protocol. It's very hard to send information using this idea, but it can be used. Protocol. So and it's actually possible to compute the channel capacity that they can, or the bit rate, quotation marks, that they get using this protocol to communicate, or that Alice has if she decides to use this protocol to communicate with Bob. Okay. The classical channel capacity is C A B. I'm gonna call it like this. Is lambda to the 4, 2 divided by log 2. All of this is in the paper that I cited up there. The SAB divided by 4 absolute value of alpha B, absolute value of beta B squared plus order lambda to the 6. And if you're scared about the fact that we're dividing by the alpha B, beta B here, remember that these are also in the definition of S. So basically, this is not going to diverge or anything. It's quite the opposite actually. But yeah, so you're not going to make this increase too much. If you set alpha or beta to 0, it's not going to matter too much. Cool. So basically, you can send some information from Alice to Bob, but this is kind of annoying because the interactions are very weak, and we're just like trying to use the interactions in a very silly way, right? We're either trying to couple or not, and then affect the excitation probability of Bob. What could we do that is a little bit better? Maybe we can even like get Alice and Bob entangled or something like this, using the interactions with the field. Can we do something like this? The answer is yes. And in order to get there, we're going to have to leave the perturbative regime. And we're going to talk about the gapless detectors that we briefly talked about last time. These gapless detectors, we can do the calculations analytically, and this is pretty good if you want to find out what happens with stronger interactions and for very long times and things like this. So let me actually title this because we're really changing topics. So maybe I should just title this non-perturbative results. So what can we say non-perturbative, right? So one can consider instead omega A equals omega B, which is 0 for non-perturbative calculations. Now, if we do that, then the interaction Hamiltonian of each one of the qubits, or the total interaction Hamiltonian, will simply be lambda mu A, lambda A of x, phi of x, plus lambda mu B, lambda B, phi of x. So now the mu's don't vary on time. Oh,
Excuse
is
me.
there something in the chat?
Uh,
Okay. Yes.
uh, uh, Excuse me. Uh, for the previous one that you said about Alice and Bob, about the classic information and causality, which you said, would you please uh, tell more information about it? For example, I want to know that we are talking about the connection that uh, we can say in a local, uh, for example, field, or no, uh, the means of causality, or you said important notation. You said that only if they are causally connected. Can you please say more about that? Because I a little confused about that. We need, the quantum entanglement. I imagine that, okay, we don't have any connection, but they have an entangle. But in a, for example, causality mode, we have a connection that we can see or send an information or receive. Would you please correct me and say,
Oh, yeah,
yeah,
sure. So in this case, what we have is both Alice and Bob, they start in a product state. So they start completely uncorrelated, right? Now, what I'm saying is that the calculations that we did here, or at least the results here, they show that if this is lambda A of x, and if this is lambda B of x, these are all space-time diagrams. So time is always up, and space is always to the yeah. Now, the calculation that we got was that the effect of A on B is this SAB, right? This is SAB, which is calculated up here. Now, what really matters for me is not the actual expression, the alpha A's, the beta B's, whatever. Just notice that this is an integral of the causal propagator, E of x prime, which is integrated, which is basically like the support of A and the support of B are basically what defines the region where this integral is defined here, basically, right? So if you integrate this dv prime of the lambda b x prime with the e of x prime, what you will find is that this integral will result in a function, which is basically the propagation of lambda b within its causal cone. So if b is defined there, the the integral dv prime of the e of x prime of lambda b of x prime, this is a function of x, which will be defined in this region of spacetime, which is basically the causal past and the causal future of b, right? Now, if Alice is not doesn't overlap the causal past or causal future of b, now the integral now if I integrate dv lambda a of x times whatever I get when I do the integral dv prime of e of x prime lambda b of x prime. Now, this will always be 0 unless Alice overlaps the causal past or the causal future of Bob. In this specific case, for these calculations, the interaction of A was assumed to have happened before the interaction of B, so A would have to be in the causal past of B in order for the excitation probability of B to change due to the interaction that Alice had with the field before. That's the idea. That's what I meant when I said that they have to
You
be
mean
causally connected.
ah
You need Alice to be in the
it
causal
means
past of B.
that the effect of the past and future of Alice and Bob affect on each other. It means
It means that Alice can only affect Bob if it's in the causal past of Bob, which is basically being compatible with causality, right? You can't really affect someone who is not in your
right.
causal
Thank you.
future, who you're not in the causal past of that. Thanks for the question. Cool. So
Thank you very much.
no worries. But yeah, this is basically the quantum field being compatible with causality. Okay. And okay, I really went to the side here. Okay. Nice. So let's go back to the non-perturbative results. How much time do we have to talk about this? Okay. I don't want to really take too much time here. I'm just gonna do the beginning of the calculation, show you the preliminary result, and then after this, I'm gonna show you some plots, hopefully, and just to show you what happens in this case, right? So this is your HI, right? The mu doesn't depend on tau. So we go back to the case where where the detector where you can use the Magnus expansion, right? So you remember that the Magnus expansion that we talked about yesterday, it says basically that the time ordered exponential of something like this will be e to the sum from n equals 1 to infinity of theta n, where these theta n's, or sorry, at least let's just do one by one because the general expression is kind of annoying. Yeah, so the theta 1 is minus I the integral dv of hi of x. In this case, we can actually already do the calculation because exactly what we had last time. So this is minus I lambda mu a phi of lambda a minus I lambda mu b phi of lambda b. The theta 2 will require a little bit more work, but not too much. The theta 2 was given by minus I, the integral dv prime time ordering with respect to a given time parameter. And now we're going to have the product of the of x. Disregard the pressure. Swallow. Doesn't. Cool. Hi of x, hi of x prime. And then the next thetas that we would have to compute in order to, sorry, this is not minus I, that was my mistake. This should be minus 1/2. Yep. And then the next terms are all going to depend on triple commutator of the fields, right? Triple commutators. Cool. How do we compute this term here? Well, now if we go back to the expression for Hamiltonian there, oh, it's up here already. The lambda comes out, of course, so we have a lambda squared which comes out, just a scalar. The mu a and the mu b, they don't vary in time, so they commute with each other even at different times. So the only thing that really doesn't commute with itself at different times is the quantum field. So basically what we're going to have here will be a theta of t minus t prime Then we're going to have a term which is going to be this term with itself, which is mu a squared lambda a of x lambda a of x prime. And the second term is going to be the first term with the a term with the b term. So mu a mu b lambda a of x. Oops. Sorry about that. All right, I'll just restart the sharing again. Well, sorry about that. Okay. Okay. Lambda, so this is the A with the B term in the X prime. Then we're gonna have another term, which will be mu B with mu A. But these two commute, they are in different Hilbert spaces, so it doesn't really matter. The lambda B of X, lambda A of X prime. Then we're gonna have another term, which is the B with B, which is the mu B squared, lambda B of X, lambda B of X prime. And all of these multiply the commutator of the field to the commutator of the field, which is the phi of x, phi of x prime. Okay. Now, this commutator of the field, we know that its value is actually I times the e of x prime, is the causal propagator. There we go. So now we can, sorry about this, let me just adjust this. There we go. So now we know that this term here is I times the e of x prime. We also know that these terms are identity, actually, because the mu is just a sigma x matrix. So these are just identities. The mu a and mu b is definitely not an identity. But now this I, e of x prime, remember also that it's multiplied by this Heaviside theta, right? So what happens with the e is that up here, it is gr of x prime. And down there, it is ga of x prime. So if you multiply it by the theta, you only get the gr, right? So basically, we're using the theta of t minus t prime times the e of x prime is just a retarded Green's function of x prime. And if we use this, now we can actually keep going with the calculation. And this will result in minus 1/2 lambda squared. And we're going to have 4 terms. All of these terms will be basically GR evaluated at different lambda A's and lambda A, lambda B, lambda B, lambda A, all of these things, okay? So these terms will be, the first one will be just the retarded Green's function evaluated at lambda A, lambda A. And there's not even an operator here because the mu A squared is just an identity, right? I'm gonna write the last term here, which is the retarded Green's function from lambda B to lambda B, which is also proportional to the identity because it's mu B squared is just itself. Now there will be 2 terms here, which are mu A, mu B, which remember, both of these act in different Hilbert spaces. And because they act in different Hilbert spaces, they commute. So we can just use mu A to one side, mu B to the other side. But the term that we're going to get here will be, the terms will be the retarded propagation from, so lambda A, lambda B, and the retarded propagator evaluated at lambda B, lambda A. So this is the theta 2. And notice that when we computed the commutator here, we obtained a term which commutes with H itself. Because in the field part, we just obtained something which is proportional to the identity, right? So the commutator of the field is just identity. And in the rest of this, what we got was mu A, mu B, or just identities. But the point is that mu A, mu B commute with the free Hamiltonian, right? The free Hamiltonian is just lambda times mu A or lambda times mu B, and mu A and mu B both commute with these things. Either they act in different spaces or something like this. So basically, this implies that the theta 3 is 0, and so are all the other theta n's for n larger than or equal to 3, basically. Okay. So now we can write down the final expression. So our unitary time evolution is just going to be the exponential of whatever we computed before. The first term we got was the I mu A. I'm going to write phi A as phi of lambda A minus I mu B phi B. Then we're going to get two terms here, which kind of, I don't care too much about them because they are just, sorry, there was a lambda everywhere. Let me rewrite this with the coupling constant, because why not? So minus I lambda mu A phi A minus I lambda mu B phi B. Then the other term was the minus I, the I, sorry, I forgot the I here, but there was an I which was coming from the propagator. There's an I. So this is I lambda squared divided by 2. And we're going to get two terms here, which are, we're going to call them delta AA plus delta BB, and I'll define these properly soon. But here's the term, which is the important term, which is the mu A, mu B. And this now this is going to be multiplied by delta AB, where so in order to have this, I think that this is to be divided by 2 in order for everything to be correct. Okay, so let me define the things that I'm using here, right? So this phi I is just the phi of lambda I. Cool. What is the delta? So you remember that gr of x prime is the advanced propagation from x prime to x, okay? So basically this term here could equally be written as GA of lambda A, lambda B. So the advanced propagator. Then this becomes GR plus GA, which is the imaginary part of the Feynman propagator. It's the delta, it's the symmetric propagator. And the symmetric propagator is simply the retarded propagator from x prime to x plus the advanced propagator from x prime to x. So now, basically using this notation, the delta ij is just denoting delta evaluated at lambda I, lambda j. And if they are the same, then gr and ga are the same, so that's why you can just write these two. Okay, the delta AA and the delta BB. And there's a circle. Okay, there we go. Cool. So now about this unitary, yeah? These terms here are just global phases. So global phases are never going to affect any physical states. They commute with everyone, can just take them out, so they don't matter, right? So they do not matter. And our unitary, ui, then can just be written as e to the minus I lambda mu A phi A minus I lambda mu B phi B. And we also get another term which actually commutes with these two, so I can just factor it as e to the minus I lambda squared divided by 2 mu A mu B delta A B. Okay, that's the unitary that will be affecting our qubits. And then, of course, we would have to trace over the field and do everything there. I'm not going to do this. This will be on the notes, the partial tracing and everything like this. I think it's more interesting to actually show you what would happen if you started with qubits in the ground state and things like this. So I have some plots of what would happen. And okay, so let's consider ball situation. Before showing so let's basic vector expression, there's moving cause spacetime bending slice. So, all right, let's. The situation is we'll consider actually even closer. Get there, very close together. Now, we will consider Alice and Bob to be interacting for the same amount of time and starting their interaction simultaneously, like at this, in the rest frame. So this will be the situation we're going to consider. This is the lambda b. This is the lambda a. We will have two parameters. One parameter, actually three parameters. One parameter will be t, which is for how long their interaction with the field is switched on. The other parameter is sigma, which is how big, how large the detectors are. And the other parameter will be L, which will be the separation between these detectors. Okay. Now, for so what I'm interested in is whether Alice can get entangled with Bob. Actually, if they interact for long times, they keep exchanging information through the field, and if they start both in the ground state, so both of them will start in the ground state. They'll be interacting with the field for very long times. And then the question is, can they become entangled in the end? Okay. So if you consider this, very, very specifically, the scenario that I'm considering is where the lambda a of x is e to the minus t squared divided by 2 capital T squared, e to the minus x squared divided by 2 sigma squared. This normalized such that this is happening here. And the lambda b is exactly the same thing but shifted by this distance L. So lambda b of x is e to the minus t squared divided by 2t squared, e to the minus x minus L, where L is a vector that the direction that it points is completely irrelevant. It doesn't affect any of the results because of symmetries. But basically, these are the two spacetime smearing functions. Also, I'm going to consider that their energy gap is exactly the same. So their omega A is equal to the omega B. Now I could just show you the plot of something that will tell us about the entanglement, and I will. I'm just gonna say that the plots will all be of the. So you guys hopefully remember about the negativity, which is the sum of negative eigenvalues of the rho partial transpose with respect to one of the factors. So remember that is the partial transpose of a density operator is always a density operator, but the partial transpose may have negative eigenvalues. Okay, so we'll show you plots for the eigenvalues of the partial transpose. Okay, and if at any point an eigenvalue becomes negative, then this means that the state becomes entangled. Okay, nice. And the last thing is that the initial states, so rho A0 is, I said this, but I'll write this explicitly, and the rho B0 is also, sorry, it is also the ground state, it's GB. But before showing you the plots, so that we have some reference, let's go back to our unitary there. So you see that this unitary basically has two parts, right? This part here, which is basically the symmetric exchange between A and B, and the other part here, which is basically the noise that the quantum field will add to the system and things like this. But this term here, just like this unitary, it's a unitary which is sigma x tensor sigma x times a number, which of course will depend on t, will depend on L, and all of these things. So what happens if you just consider this unitary? So the first plot that I'm going to show you is how do the eigenvalues of these of the partial transpose of the density operator, which is the final state. How do they behave if you just use the unitary u tilde I, which is e to the minus I divided by 2 mu a mu b delta b. This is a very standard unitary. It's very simple to compute this. The only thing is that, of course, the delta b here is coming from the delta of lambda a, lambda b, which will involve all of the retarded propagation and everything like this. Okay, so let me try to share this. All right. Yes, this should work. Let me just go back to Zoom. So there we go. So this is what you get. Hopefully now I can see the screen. So this is for the auxiliary one, which is just like, let's see what happens if we just apply this unitary, right? Without the noise added by the quantum field or anything like this. So we see that there are four eigenvalues, of course. This is a 4x4 density matrix, right? And one of them is always negative except for the initial state itself and like some states which differ by a period, right? So okay, so basically that unitary can entangle the states. As a rule of thumb, that unitary always entangles the states. Okay. And yeah, that's basically it. Cool. So this is what happens with this unitary. Now, what happens if you apply the unitary with the quantum field in the vacuum state in Minkowski spacetime? This is what you see. So it's very similar. It's very similar in the sense that you still have the back and forth. You almost always get an entangled state, at least after a certain time. So you can see that basically this thing is always negative, apart from some very small regions. Now, basically what happened here is that there was a gap that was created between the sines and cosines, basically functions that were the case without the quantum field noise and things like that. Also, there was a shift up here and a shift down to this one. Doesn't matter as much. But the most important thing here is the quantum field will also become entangled with these two quantum systems, and then they can't become as entangled with each other. So that's why, like, you see that the minimum of this plot here is at minus 0.4, right? If you go back to the other plot, it's minus 0.5, right? This is the minimum of this plot. So basically, because the systems become entangled with the quantum field, they cannot become as entangled with each other. That's the idea. Okay. And also, if you look just at the very short time regime where the two are space-like separated, basically, right? Then you see that for t sufficiently smaller than L, this is of course a plot of the sorry, I forgot to say this, but the point is that the horizontal axis here is for how much time were the detectors coupled to the field compared to their separation, basically, right? So it's basically the interaction time of the detectors, if you will. Now, the point here is that for very short interaction times, when the detectors are close to being space-like separated, then you see that they cannot become entangled. But after some point, they exchange enough information with each other that they can become entangled. Okay. All right. So basically, going back to the picture there. Going back to this picture, the horizontal axis is how large this t is compared to the separation between them, right? If the separation is very large, they have a lot of time to exchange information through the field. They can actually become entangled with each other. But there's always the noise that these terms here, that this term basically introduces, which always prevents the detectors from becoming fully entangled with each other. They're always a little entangled with the field as well.
Excuse
Okay.
me.
Yeah.
I have the same question exactly. If we, in a imaginary experiment, one of the frame, for example, Bob, start to moving and as a detector, lambda b becomes we have a x minus l, uh, and for example, at the first it's bouncing. Uh, First, what happened? It's the noise that you said will affect on the information between Alice and Bob. Mm, I mean that Alice is in his place, and Bob start in the frame of Bob start to bouncing and go far away. The first one, and the second one, if the second frame goes to the infinity, the lambda b will be changed. Yes, and what happened to the information and the noise um, between Alice and Bob?
Okay, so when you say infinity, do you mean spatial infinity or what?
First, the frame B start to moving and far away from frame one, and bouncing close and far. And the second one,
No, wait.
the
So if frame B is moving from
frame
if
B
Bob is
start to go to the infinity.
okay, so this is what it would look like if B was moving with respect to Alice, right? So this is the situation you're asking about, right?
Yes, exactly, exactly.
Okay, fair enough. No, I don't know. I have the results. I can well, I can tell you that I mean, if this parameter here, sorry, I shouldn't be using this color, but if the t parameter is long enough, I would expect them to still be able to exchange information. But that's a good question regarding the like the back and forth between them will take longer on the way back, basically, right? And then that'll be interesting to see. I have the analytical calculation for all of this done. I can definitely plot the eigenvalues for this case and send them to you later, or even show them in the beginning of the next lecture next week. But this is an interesting question. I don't know. I don't really think that anyone has evaluated the long time limit in the non-perturbative regime um in this case. But yeah, this is a good question.
Thank you very much. Thank
No worries.
you. Thank
Well, this is what I want to tell you. Um, Tomorrow our goal will be to talk about animal harvesting. The human harvesting is an idea where basically the two detectors will interact in space-like separated regions. So the detectors will be causally disconnected, but still there is a probability that there's a chance that these detectors will end up entangled with each other in the end, although they are in space-like separation. So in this example we saw today, this doesn't happen if the detectors are if detectors are space-like separated. We saw no entanglement in the beginning of the plot, but then eventually they get in causal contact. They start to exchange information through the field, and they become entangled. Tomorrow we're going to see where the detectors do not have to exchange information through the field in order to become entangled, which is this thing called entanglement harvesting. Okay. But yeah, that's it. Any other questions? Right. If not, then thank you very much for
Excuse me,
coming.
next session is on Monday, yes? Or
Yeah,
tomorrow?
I was about to say this. So the next lecture is not tomorrow. It's on Monday next week. The next two lectures
Uh-huh.
are Monday and Tuesday next week. Same time as this one started.
Okay.
Next lecture we talk about entanglement harvesting, and the other one we'll talk about the everything that I've been sweeping under the carpet regarding entanglement harvesting. So, oh, sorry, regarding the particle detector models and causality and relativity and time parameters and all this. So we will discuss all of these in the last lecture. Okay, cool. So thank you very much, and I guess that's it. We can stop the recording, but I'm not recording this time. Bye bye.